It's always a great pleasure to be in Paris. I was delighted to be invited. Thank you to the organizers. For the next 45 minutes, I'm going to talk about profinite isomorphism problems. Problems, there'll be three of them. Okay, so there's three distinct problems I want to talk about, and in some sense, they're all about isomorphisms, or recognizing isomorphisms between profinite groups. So the first problem, which is the most fundamental to my point of view, it isn't really a problem about profinite groups at all. It's a problem about discrete groups, a classical problem. So, of course, in the middle of the 20th century, so the first great wave of achievements of combinatorial group theory was the proof by Novikov and then Boone of the undecidability of the word problem for finitely presented groups. And then once you know how to construct finitely presented groups that have unsolvable word problems, then there's what now seem like fairly routine methods using HNN extensions and amalgamated free products to take a group with an unsolvable word problem and then do various constructions using such a thing and unsolve lots of other problems in group theory. So there's nice, Adrian and Rabin wrote this out nicely, and it's so-called Markov or properties, if a Markov property is undecidable. So most properties of finitely presented groups are undecidable in the absence of further hypotheses. So if I give you a finite presentation of a group, like maybe that one, and ask you, is that the trivial group? That's to amuse experts. I'm not going to tell you whether that's the trivial group or not. There's no algorithm you can apply. You might be clever with any given example, but there's no algorithmic procedure you can apply to decide if a group is finite if a group is finite or trivial or abelian or whatever. Okay, but there's one. There's one particular problem that I've been fascinated with this by a long time that seems to be of a different nature. Okay, so this one doesn't follow easily from those classical considerations, and it's this. So does there exist an algorithm so that if I give you a finitely presented group, then you can decide whether or not that group has a non-trivial finite quotient? Okay, so how about that one again, for example? Does that have a non-trivial finite quotient? So that's the first and the main problem I'm interested in. So does there exist an algorithm that will let you decide whether a given finitely presented group has a finite quotient or not? So let me try and use this thing. Okay, now, you might phrase that. So the title is Profinite Decision Problems. So it's really a problem about discrete groups, right? But you might phrase it by saying this is the profinite triviality problem. So if I give you a finite presentation of a group, instead of thinking it as a discrete group, you could think of it as a profinite group, or equivalently take the profinite completion of that group, and then you'd be asking, is the profinite completion of that group trivial or not? Okay, so you can think of that problem about discrete groups as the triviality problem for finitely presented profinite groups. You can think of it like that, but that's not helpful for this particular problem. Okay, so that's not how I'm going to attack it, but it is useful. It's a useful observation to embed it in various applications. So that's the first problem I'm interested in. But I've already used the words profinite completion, so this is somehow one of those definitions that passes you by. And the first few times it's hard to absorb, maybe, and after a while it just seems so obvious that why would anybody not absorb it? So hopefully you will all absorb it. So the profinite completion of a group. So you just look at all the look at all the finite images. Those naturally form an inverse system, and you take the inverse limit to that thing. Okay. So what you gain? Well, you take some nice countable discrete group like Z, and you trade it in for some uncountable group, and that doesn't seem like progress. And the progress is you gain topology. Right? This is naturally a compact group because these are finite groups, so they're compact topological groups. You've taken an inverse limit, so it's still compact. So that's a compact topological group. That's what you've gained. And so some basic facts. There's a compact group with the same finite quotients as gamma. So I'm assuming gamma is finitely generated here to avoid problems. There's always a natural map. There's an obvious map from a group to its profinite completion. And that'll just by definition be a dense subgroup, the image of that map. But it won't always be injective. Okay? So this gamma hat, it's built out of the finite quotients of gamma. So in particular, if gamma doesn't have any finite quotient, for example, then there's nothing there. Okay? So you can't hope to see the whole of gamma in it. And in fact, you see the whole of gamma, the natural map from gamma to gamma hat is injective, if and only if your group is residually finite. That is to say, every element survives in some finite quotient. Okay, so that's, and so that this is a nice functorial procedure, so it really is a completion in the obvious sense. So any homomorphism of discrete groups will induce a continuous homomorphism of their profinite completions. Okay, and so we'll be needing that. So I'll be talking about maps like that. So whenever you've got a map between discrete groups, you can consider the induced map between their profinite completions. And here is a rather, this looks like a rather perverse thing to do, but I'm just going to say it anyway. So that nice natural problem of does a group have a finite quotient or not, you can rephrase that by saying, given a group gamma, can you decide if the inclusion of the trivial subgroup induces an isomorphism of profinite completions? Okay. Now I'm saying it like that because it connects it to the other two problems that I'm interested in. Okay, so the second problem I'm interested in is the isomorphism problem. Well, there's various things you might mean by the isomorphism problem. So I'm going to mean this. So the isomorphism for finitely presented profinite groups, or the recognition problem, is if I give you a pair of finitely presented, residually finite groups, and I ask you, okay, there's a map between them, does that induce an isomorphism of profinite completions? Okay. So can you recognize an isomorphism when you're given one? Or you might say, well, okay, or can you even tell if the two things I gave you have isomorphic profinite completions or not? Okay? So there's a version where you've got actually given a map, and you're asked, does that induce an isomorphism? And there's a version where you just say, here's two finitely presented groups. Do they have the same profinite completion? Or in other words, do they have the same finite quotients? That's an equivalent question. Sorry, yeah, so that's a good point. Yeah, I really do mean, Laurent's making a good point. So when I say a finitely presented profinite group, I might mean that the relations are given by infinite words. Here I'm talking about the profinite completions of discrete groups. Yeah. So my presentations really have got things like on the board there. Okay. So you take a discrete group, you take its profinite completion. Okay. So so I want to know, can you recognize isomorphisms? Now you have to always be careful what given means. Okay. So here I'm given all those words: finitely presented groups, a pair of finitely presented groups. I'm told they're residually finite, so I'm allowed to build an algorithm that uses that as an a priori assumption by searching finite quotients or something. And I'm given the map from P to gamma. Okay, so I have to say where you send the generators of P in gamma. Okay, so that's what I mean by given. There are variations on how you might be given this information, but that's what I want to consider, the most natural problems. You're given finite presentations, you're given the map. Okay. Now, this wouldn't be an interesting problem if the answer were always obvious, as it were. So this will only be an interesting problem if there are non-obvious maps between finite presented groups that give isomorphisms of profinite completions. Okay, so and if so you don't want this just to reduce to the isomorphism problem for discrete groups. You want to really do. Now this is only interesting if there's a real difference between isomorphism of abstract groups and isomorphism of profinite completions. So that was an issue for quite a while, raised by Grothendieck in 1970. And so the first construction of pairs like this was in this paper of myself and Fritz Grunewald in 2006. So there do exist pairs of finitely presented, residually finite groups, so that the inclusion of one into the other gives an isomorphism of profinite completions, but the groups aren't isomorphic. Okay? So there really are interesting examples. And now, what we're really exploring here is, okay, as soon as you've got one construction of examples, you want to know what's the universe of examples, right? And we're hoping the universe of examples is rich enough or diverse enough so that problems become undecidable, right? That's kind of that's an honest way of proving that there are lots of these things, right? That you want to see that there are enough pairs, these so-called Grothendieck pairs, there are enough pairs of finitely presented groups like this so that you can't decide isomorphism. Okay. So that's the second problem I'm interested in. I should write these problems down. So the first problem is the profinite triviality problem, where I want to know is something trivial. The second, I've got a map between finitely presented, residually finite groups, and I want to know, is U an isomorphism? Okay. And what's the third problem? Well, the third problem goes back to this business of once you've got one example, you want lots of examples. So when Fritz and I proved this theorem, there was something we really wanted to do and we couldn't at the time. And that was we would like to have fixed gamma and constructed infinitely many different finitely presented subgroups that have the same profinite completion. Okay? So can you do that? So if you fix a finitely presented residually finite group gamma with finitely presented, can you construct a sequence of finitely presented subgroups that they're all different, but that all of the inclusions induce isomorphisms of profinite completions? Okay, so as discrete groups, they're all different. They're all sitting inside an ambient thing, but profinitely, they're all the same. Okay, can you do that? And this is, so if two things have got the same profinite completion, you say they've got the same profinite genus, or strong genus, if there's a map inducing the isomorphism. So the way this can be phrased is, can the strong profinite genus of a finitely presented group be infinite? Okay, so that's the infinite genus problem. So those are the three problems. So that they're all sort of isomorphism problems. Okay, and those are what I want to talk about. Now, if I couldn't solve these problems, this would be a short talk. Right? I would just stop here. So there's three problems. Can you decide if an abstract group's got a finite quotient or not? Can you decide profinite isomorphism? Can you construct groups with infinite profinite genus? Well, where are the theorems? What are the ideas? And where is the geometry? Yum, yum, yum. Geometry in red. We always need geometry to get us out of bed in the morning. Okay, so this is sorry?
Random walks.
Where are the random walks? They were in your talk. Yeah. So, yeah, that's a good point. Yeah, there's no random walks. Sorry. Okay, so here are the theorems. So the first two, what I'm discussing is I put three preprints on the archive in January. The first two are joint with Henri Wilton, and they correspond to these three problems. This is in the paper with Henri Wilton. So that this whole problem about can you recognize if a finitely presented group has a finite quotient or not is unsolvable. Okay? So there does not exist an algorithm that, given a finitely presented group, can determine whether or not that group has a finite quotient, or equivalently, whether or not that group has a proper subgroup of finite index. For experts, so if you never thought about decision problems, what are you trying to prove? It always comes down to proving that some indexing set is recursively enumerable but not recursive. Okay, so there'll always be, you'll be asking a question yes or no, and the set of inputs for either yes or no typically will be something you can list. Okay, so in this case, if I give you a finitely presented group and say I'll give you $1 million if you can find a finite quotient, there's kind of a stupid thing you can do. You can just enumerate all finite groups. You can enumerate all maps from this group to all finite groups. And if there is a finite quotient, you'll eventually find it like this. You can't fail. You will find it. Okay, so then what's undecidable? What's undecidable is there won't come a moment where you can stop and not say I'm tired, but say I've now proved there is no finite quotient. Okay, so that is the element of undecidability. There's no moment at which you know that you're going to fail. So more precisely, there is a recursive sequence of finitely presented groups. So the set of integers which do not, no, got that wrong. Sorry, yeah, let me try that again. There's a sequence of finitely presented groups so that the indices where you do have a subgroup of finite index, it is recursively enumerable. If there are finite quotients, you can find them, but it's not recursive. That is, you can't enumerate its complement. Okay. And I'm going to try and illustrate why I think this is an important result. So I'm going to try, in passing, to give you some applications of this. Okay. Now, typically, if you're trying to prove a problem is undecidable, you think you're going to go out into this wild universe of finitely presented groups, and you're going to be dealing with really crazy groups that you're going to manufacture. And that's true. But in good situations, if you're lucky, or you work hard, or both, you can drag those undecidability results into areas of group theory where you have nice structure, nice geometry. And this is one of those cases. Okay, so these groups where you can't recognize if they have finite quotients or not, a priori you build these rather crazy groups, but you can then adapt the construction so that curvature doesn't help. Now, in a lot of decision problems, curvature helps. If you deal with groups, if you restrict your attention to groups that are fundamental groups of compact, non-positively curved or negatively curved spaces, then often difficult decision problems become accessible. Right? The great example being Zeller's theorem that the isomorphism problem for hyperbolic groups is solvable, for example. But this is not one of those settings. In this setting, curvature really doesn't seem to help. So in particular, you can, so Henri and I actually proved there's no algorithm that, given a compact, non-positively curved squared complex, for example, can determine if its fundamental group has a finite quotient. Or topologically, let me just say this, just, as I said, I want to indicate why you might care topologically or geometrically. If I hand you a compact, non-positively curved squared complex, there is no algorithm you can apply to determine if that thing has a finite sheeted covering or not. Okay. Just as an aside, this is obviously relevant to the problem of deciding which cat-zero complexes are virtually special. But I don't know yet if that's undecidable or not. Oops. Okay. Oops. Well, I just did something weird there. What happened? Okay. So for hyperbolic groups, okay, we can't do this for hyperbolic groups, but and there's a basic reason for that. We still don't know, right, whether hyperbolic groups are residually finite or not. If there exists a single hyperbolic group which is not residually finite, then you'll be able to prove the analog of this theorem for hyperbolic groups. Okay, so if there's a hyperbolic group that's not residually finite, then in fact you will not be able, then there will be also hyperbolic groups that have no finite quotients, and you will not be able to tell, given a hyperbolic group, whether that hyperbolic group has a finite quotient or not. Okay, so that's just a conditional remark, but you can use these techniques to prove unconditional theorems about hyperbolic groups. So, there's several of them. Here's one of them. So it does not exist an algorithm that, given a hyperbolic group, can decide whether or not that group is large. Okay, so largeness is a very interesting property for groups. It's played a prominent role in the recent work of Agol and Wise, for example. So if I give you a hyperbolic group and ask you, does it have a subgroup of finite index that maps onto a free group, you can't tell. Okay? That's an undecidable problem. Right. So that was all around the first of these problems, deciding which groups have no finite quotients. Around the second problem, so that's also unsolvable. So there are recursive, so let me say it colloquially, and then it's written in a technical way on the board. So given a pair like this, okay, I hand you a pair of finite presentations of groups. I promise you they're residually finite. I give you a map between them, and I ask you, does that map induce an isomorphism of profinite completions? That's an unsolvable problem. Okay? There is no algorithm that can solve that problem. Also, if I just ask you, given that same data, is the profinite completion abstractly isomorphic to the profinite completion of gamma? In other words, do P and gamma have the same finite quotients? that's also an unsolvable problem. So that's what's written up there. So blah, blah, blah. So those are the two problems that again, there's this business of the index set being recursively enumerable but not recursive. So what's easy this time? There's always one direction of these problems that's easy. If they have different finite quotients, then you'll be able to find the one that's a quotient of this one but not of this one, for example. Okay? So the set where it's not an isomorphism you'll be able to enumerate, but you won't be able to enumerate its complement. There won't come a moment when you'll say, oh, I've stopped, I've checked up to the number of atoms in the universe, and I've decided they have the same finite quotients. Okay? That's the unsolvable bit. And you also, so what this comes down to is you can't determine whether the induced map of profinite completions is an epimorphism, whether it's surjective or not. And once again, you can encode this into reasonably nice groups. So it's not like these are crazy groups that have no nice geometry. So in fact, you can make it so that the bigger group, gamma n, is actually the fundamental group of a product of two negatively curved two complexes. Okay, so it's a product of two nice hyperbolic groups. So that's the second problem. The third problem, which is in this third paper on the archive, so that again, things are as bad as you might hope if you're looking for more employment in future years to come. So there do indeed exist finitely presented, residually finite groups where you can construct infinite sequences of finitely presented subgroups in that one fixed group so that they all have the same finite quotients. They all have the same profinite completion, and the inclusion maps induce isomorphisms, induce those isomorphisms. Is everyone happy? Does everyone absorb those theorems? So is that's an unsolvable problem. That's an unsolvable problem. The infinite genus problem, there exist groups of infinite genus. Okay, in this strong sense. So that's what I want to talk about. Okay? So those are basically the results that I wanted to tell you, and I hope I've told you in a way that they make sense. The definitions make sense. And so what am I going to do with the rest of the time? Oh, we could just have coffee. But here's the plan for the next 20 minutes. So I'll describe the main ideas, or I'll at least wave my hands at the ideas. How do you solve this main problem? If I give you how do you know that given a finite presented group, you can't tell whether it's got any finite quotients or not? Then I'll indicate something I haven't said yet, how, when you've proved this problem's unsolvable, how by refining that solution, you can get to this isomorphism problem being unsolvable. And then, if time allows, I've just got a slide or two at the end to explain the ideas that go into constructing these groups of infinite genus. Okay, so this is a moment that you can just take in isolation and think about this. Now that there is visibly a sentence in the first order theory of groups. Okay, that is a statement about a group. You give me a group, that may or may not be true in your group. So what does this say? So let's read it together. For all four elements, so take a group G. Take any four elements in that group and consider whether the following sentence is true or not. This sentence says, given any four elements, either when you conjugate A by B, when you conjugate A squared by B, you don't get A cubed, or when you conjugate C squared by D, you don't get C cubed, or the commutator of A and B is not equal to D, or the commutator of C and D is not equal to B, or A, B, C, and D are all trivial element. Now you might not have got up this morning caring about that sentence, but you can't deny that is a sentence in the first order theory of a group. Okay. Now, why might we be interested in that sort of thing? Well, the key observation is that that sentence is true in a given group G if and only if, I hope I've got this the right way around, there is no non-trivial homomorphism to that group from this group B. Okay, let's work at that. So what would a homomorphism from B to G look like? Well, you'd have to send the generators of B to some elements of the group, which would then play the role of A, B, C, and D. If this were really a homomorphism, then this relation would be trivial, which means that bracket wouldn't work. This second relation would have to hold, which means that second bracket wouldn't work. This third relation would have to hold, which means that doesn't work. That fourth relation would have to hold, which means that wouldn't be true. And so the only conclusion would then be that this was the trivial homomorphism. Okay? So if that sentence is true, then the only homomorphism from that group to G is the trivial one. And that's exactly what that sentence expresses. Okay? That sentence is true if and only if there is no non-trivial homomorphism from B to G. So we see that first-order logic, in fact, just this simple, or this reasonably short, one quantifier sentence expresses that idea. Okay? That one sentence captures the idea that there's no homomorphism from this group to your given group G. So if that sentence is true in all groups, what does that mean? Well, that means there's no homomorphisms from B to anything, well, in particular to itself, so it means the group's trivial. Right? So that sentence up there will be true in all groups if and only if that group is trivial. So it's a sentence of first-order logic that's the first-order logic of groups that says whether or not that group is trivial. By the way, I've called something else B over here. It looks different, but it's not. Okay, this is actually the same group here, right? And so if you've done the exercise in the first part of the lecture, you'll know by now whether that group's trivial or not. That sentence is true in all finite groups if and only if B has no finite quotients. Okay, by the same logic. Now this is now getting interesting, right? Because this is relevant to our problem, right? That sentence, it's true for all finite groups if and only if B has no finite quotients, i.e., that sentence interpreted in the theory of finite groups is equivalent to whether or not the profinite completion of B is trivial. So this profinite triviality problem is now seen as a problem in the first-order theory of finite groups. So in fact, for those few of you who haven't yet done the exercise, I hope this isn't working. Oh dear, what's happened? In fact, that group isn't the trivial group, but it does have trivial profinite completion. Okay, I like this group a lot because it's the smallest one I know. It's 3 generators and 3 relations, and it has no finite quotients. Okay. So we see that deciding if things have finite quotients has got something to do with the first-order theory of finite groups. So in fact, though there's nothing special about that particular presentation there, other than I want to do it explicitly, if I took any finally presented group, I can write a first-order sentence. Oh, this battery just went. I could write a first-order sentence that express whether that particular finite presented group has any finite quotients or not. And so then it's an easy lemma to see that if the profinite triviality problem is unsolvable, that is to say, if there's no algorithm that can decide if a finite presented group has a finite quotient or not, then the first-order theory of finite, so even the universal theory, there's only one quantifier, the universal theory of finite groups would be undecidable. That is, given a sentence, like the one on the previous board, you wouldn't be able to decide whether or not it's true in all finite groups. Okay? So there's a possible way of approaching this problem. But Slobodskoy's already done this. Okay? So this would be a way of proving that the first-order theory, the universal theory of finite groups is undecidable. Prove the triviality problem is unsolvable, which is what we're trying to do, and then you'll be able to deduce that the first-order theory, the universal theory of finite groups is undecidable. But Slobodskoy's already done that. He did it in 1981. He proved in a different way that the universal theory of finite groups is undecidable. So what would we obviously like to do now? We'd like to reverse the process. Okay? So instead of using the profinite triviality problem to deduce that the universal theory of finite groups is undecidable, we'd like to try and go the other way. Okay? Now, Slobodskoy didn't do it like this. What Slobodskoy did implicitly was what one might call a profinite word problem. So this isn't how he stated it, but this is all there in his paper, that there's a finitely presented group for which there is no, so that for this particular group, there's no algorithm which, when you're given a word in the generators, instead of asking, is that word like the normal word problem, instead of asking, does that word equal the identity, ask, does that word equal the identity in the profinite completion? Okay? In other words, ask, does that word die in every finite quotient of the group? What he did was prove that that problem is undecidable. And it's an easy exercise after what was on the previous board to see that that can be written out as a first order sentence. Now, his original group was actually kind of built out of a Minsky machine, and it had an unsolvable word problem. But actually, after what I've done with Henri, you can even take such groups to be cat zero. Okay, so what's the plan? So the plan is you'd like to take Slobodskoy's theorem and promote it to unsolve the triviality problem. So in the discrete world, the analog is, given a group with an unsolvable word problem, you then do various constructions based on this group, and you try to construct a sequence of groups parameterized by words in the original group so that you can't decide which of these new groups is trivial. Right? So you make it so that the new group you've built is trivial if and only if the word that indexed it was the identity in the original group. Okay, and you do that by just taking a sequence of HNN extensions and amalgamated free products of the original group, where the amalgamated things are always free groups and cyclic groups. That's a slight lie, because you're going to end up with the trivial groups. You can't quite be taking amalgamated free products and HNN extensions, but that's basically what's true. Now, that's all quite straightforward from a modern point of view, but in the profinite setting, it doesn't work. Because you can't just take a group and start taking HNN extensions and amalgamated free products and expect to preserve something like residual finiteness or preserve the nature of finite quotients. For example, that group B over there, our friend B, so this is the 3-generator 3-related presentation, but in fact, the 4-generator 4-related presentation expresses it as an HNN extension of a cyclic group amalgamated along with a free group with another HNN extension of a free group. So abstractly, you can't hope to get anything better than that, right? That's a graph of groups where you're just doing HNN extensions and amalgams along free and cyclic groups. But that thing's got no finite quotients. Okay, so, and what that's a sort of extreme illustration of is when you start forming graphs of groups, even out of nice groups, it's hard to control the finite quotients. You might lose them all. Okay, okay, bear with me. And I know this is a bit technical. I was agonizing over what to say about this. But nevertheless, this is sort of the only game in town. So the idea is you're going to take a group like Slobodskoy gives you. So you've got a finitely presented group where you can't tell which words die in the profinite completion. Then you're going to do things like HNN extensions to stick all the generators of your group, make them conjugate to this mysterious element that you don't know if it dies or not. And you're going to have to do all of this whilst controlling the finite quotients. Okay? Now, problems like this have been very prominent in group theory recently, and it sort of goes back to John Stalling's proof of Marshall Hall's theorem for free groups, and these graphical and geometric techniques for proving that things are residually finite or subgroup separable. And there's sort of well-defined things that you have to achieve on the way. Right? You have to prove that various subgroups will be separable and will be closed in the profinite topology. You have to manufacture things so that you don't get bad situations like this, but instead, when you're doing amalgams, you have to make sure the things you're amalgamating along are malnormal. You need to keep properties like omnipotence, which is an idea due to Danny Wise. So he proved that free groups are omnipotent, and then later extended that to much larger classes. And so what's omnipotence? Omnipotence is this wonderful thing that's it's non-trivial even for free groups. You all know that free groups are residually finite, but suppose you've got your 6 favorite elements of the free group, and none of them are conjugate to powers of the others, and you say, well, I'd like to find a finite quotient where these 6 elements have orders P1, P2, up to P6. Well, you can't quite do that, But say you pick your favorite numbers and then say you want to do it projectively. So you at least want there to be a constant so that the orders of your favorite 6 elements in some finite quotient have the right ratios. Can you do that? Can you prescribe orders of elements and quotients of free groups? That's called omnipotence, so it's an idea due to Danny Wise. And you can do it in free groups, and we need it in more generality here, so we soup that up a bit. So those are the techniques, okay? It's graphical, geometric techniques, going back to Stallings, and extended greatly by Wise. Okay. So it's topological and geometric. Okay, that's sort of the headline. Sorry. Okay, how long have I got? Just 10 minutes. Okay, thank you. Okay, so that's all I'm going to say about this. Okay, so it is take the groups Lebowski gives you, do various H&N and amalgamated constructions, but you really have to use these constructions, the sort of constructions that have been used a lot in connection with special cube complexes and so on in the last few years. So let's go to the isomorphism problem. Now, before I come to this, so it's not obvious why you want to do this, what's on this sheet. But what I'm trying to do now is say, okay, can we take what we've learned here and now unsolve the isomorphism problem? Okay, so I want to somehow, you see, in some sense, well, this is an isomorphism problem, right? You're trying to decide if the given finite presented group is profinite equivalent to the trivial group. But this is a very different problem. What's specified here, remember, is these groups have to be residually finite. So it's not a matter of collapsing and seeing nothing in the finite quotients. What you're required to do is prove that when you've got a map between residually finite groups, you can't tell if it's an isomorphism. So you will be able to see arbitrarily large pieces of the groups in their finite quotients. Okay, so you're not losing information by looking at finite quotients, but still, it's hard to see whether P and gamma have the same finite quotients or not. And so I'm going to sketch the proof of how you unsolve this, but I also want to make the point that I made earlier. So we already saw you could sort of impose non-positive curvature in that situation. I want to sort of show you another example where you get more geometry and topology into the situation when you're considering profinite triviality. So here's a souped up version of that first theorem. So let's read this slowly. So there's a recursive sequence, you can construct of finite combinatorial complexes so that they're all aspherical. Okay, so they're contractible universal covers. They're superperfect, that is to say H1, just like my children, H1 equals H2 equals 0. Okay. And there's no algorithm to say which fundamental groups have trivial profinite completion. Okay. Or said differently, so this is really a topological theorem now. So you can, so what's the topological problem? Given a compact aspherical complex, can you decide if that complex has a finite sheeted covering or not? And the answer is no. Okay. But we've got these extra conditions. It's not clear for the moment why I want them, that you make it so that H1 and H2 of the complex are 0. Okay. So I'm going to sort of sketch a proof of this. Well, I'll say a few words about the proof of this, and then I'll explain what this has got to do with profinite isomorphism. So first of all, I mentioned before that you can do a cat-0 variation on our basic construction. So you can prove a theorem like this without the second condition. Okay? So the cat-0 version of our main construction will give you a sequence of cat-0 complexes, which are aspherical, and you can't decide which ones have the étale fundamental group's trivial, where the profinite completion is trivial. But you can't control H2. In fact, in that construction, there'll be lots of 2 cells, and automatically H2 will be very large. Okay? So how do you remedy that? Well, there's an obvious standard trick for getting rid of second homology you don't want, and that is you pass to the universal central extension. Okay, you've got a perfect group. There's this thing, you just take the universal central extension of that group, and that will give you a group whose second homology then will be 0. So remember, whenever you've got a perfect group, there's always a short exact sequence that constructs this universal central extension whose kernel is H2 of G. And this group in the middle will be, if that's perfect, that will be super perfect. Okay? The second homology of the universal central extension is always 0. So we'll do that. Now the trouble is, if you take something, you take its central extension, then you push up the dimension. And even if you've got a nice classifying space for the thing you started with, how can you construct a nice classifying space for the central extension? In general, that's an undecidable problem, but in this context, it's not. So you have to do this in an algorithmic manner. So I give you a finite presentation. You run an algorithm and give me back a finite presentation for the universal central extension of that group. And then you have to build a geometric model for it. Okay? So in this context, these homology groups will be free abelian groups. And so if you've got a nice classifying space for that, then you've got a classifying space for this by some sort of torus bundle over the original complex. But you have to do all this algorithmically, so you need an algorithm that will construct a certain type of aspherical torus bundle over the original complexes. Okay? So this is obviously a more topological thing, but that's how you prove that theorem. Okay? So this is how we're trying to push this theorem out into other contexts. Okay? So going from the profinite triviality problem to these more topological constructions. Now, why do we care? Well, you might not care, but I do. So why did I care to make the first and second homologies 0? Well, it's because this is how you build pairs of finitely presented groups that have the same profinite completion. Okay? There's really only one known construction for making finitely presented pairs like this. Well, there's several constructions, but they're all variations on the same theme. And it's this construction that's in my paper with the late Fritz Grunewald. So how do you make a pair of finitely presented residually finite groups so that the inclusion induces an isomorphism of profinite completions? Here's a cartoon of the proof. You start with a group Q that has a finite classifying space. Right? So that's going to be these things here. We're just building finite classifying spaces for groups. You need a group with a finite classifying space that has no finite quotients. Okay, again, back to the previous slide. Good, that's what we did. Okay. And you have to make it so that h1 equals h2 equals 0. Good, that's what we did. Okay, so that is all to fulfill the first line of this construction of my paper with Fritz. So we're going to have a construction, and the input has to be a group with a finite classifying space, trivial profinite completion, h1 equals h2 equals 0. You then use a RIPS construction. Nice to see you here today. This is actually, I say a RIPS construction. There are lots of variations on the RIPS construction where you get extra properties, but here you can just actually now use the original RIPS construction. So there's this beautiful, very elegant construction where you feed in an arbitrary finitely presented group. I hope you all know this. And instead of, and you get a two-dimensional, a small cancellation group mapping onto it with finitely generated kernel. Okay, and now, after the work of Wise and Agol, you know that that small cancellation group will actually be residually finite. So you take Q, you feed it into that short exact sequence. You've now got a hyperbolic group mapping onto it. Now you take a fiber product. That is, take the set of pairs in H cross H that have the same image in this horrible group Q. Why would you do that? Well, because there's a theorem called the 1, 2, 3 theorem of Baumslag, Bridson, Miller, and Short that tells you that fiber product will be finitely presented. That's not obvious. It uses the fact that these groups have finite classifying spaces. Okay. But that's a way. So now what have we got? We started with a bad group Q, and we've now got a nice group, a hyperbolic group, and a finitely presented subgroup, and somehow this is keeping the badness of Q. The badness of Q has gone into this pair, P sitting aside H cross H. And then you argue that because Q had no finite quotients, then you adapt an argument of Platonov and Tavkin to say that the inclusion induces an isomorphism of profinite completions. Okay. But that would be true if and only if the original group had no finite quotients itself. So that's the template. Okay? And that is why we went to the trouble on the previous slide of constructing groups with these properties. So you're feeding in these groups, they have all the properties except maybe they have some finite quotients, and maybe they don't. So maybe the inclusion of this fiber product induces an isomorphism of profinite completions, and maybe it doesn't, and you can't tell. Okay? And so that's the end of the proof. You just feed the fundamental groups of those aspherical complexes into this machine, and what you get out are pairs of groups where you know they're residually finite, but you can't tell whether the inclusion is inducing isomorphism and profinite completions or not. I know I'm out of time, so here's the one slide on theorem 3, the infinite genus problem. I can now tell you, because I've sketched this basic template that comes out of my paper with Fritz, you're again going to run some version of that, but you're going to need to construct some new bad groups Q to feed in. And what are the new bad groups Q? You're going to construct a non-Hopfian group that has a finite aspherical presentation and no finite quotients and is superperfect. And it's based on that group B I have over there, my friend B on the board. Okay? There's some other ideas there about Nielsen equivalence and asymmetry in fiber products, but I'm out of time, so I'll stop. Yeah.
Thank you, Martin. Are there any questions, any comments in the audience?
So what did you refer to attention to, like, solvable questions, like crossover completion? Is there anything to decide about it?
Finite solvable, you mean? Or do you mean finite solvable or Pro P?
I guess everything is decided also on your time, right? Maybe not.
Yeah. Yeah, no, sorry, yeah, no, it's just, no, that, yeah, so, no, it's just, no, sorry, that's easy. No, so you can see if something's, you can just see by abelianizing whether something has a finite p quotient or not. So, yeah, so the triviality problem's trivial. That's right, yeah. Yeah, and likewise for solvable. Yeah, yeah. So no, again, you'll have an abelian quotient. So, and abelian quotients you can see. Yeah.
Is it possible to decide whether there's a quotient which belongs to a certain series of finite simple groups?
Now that's a good question. I'm puzzled about this actually. So, so this, if you think about this theorem, it tells you that for one of the infinite series of finite simple groups, for at least one, there's no algorithm that will tell you whether a given finite presented group maps onto one of the groups in that series. So for some series. For some series, right? That's what the theorem says. Now, I'm interested. So, take the alternating groups, for example. It's probably true that you can't tell if a finite presented group maps onto some alternating group. But I can't prove that. And this line of argument doesn't help you. So take the families, take the classical finite simple groups. There should be a theorem for each family. And we know that in one case it's undecidable. Maybe it's undecidable for them all, maybe it's not. I don't know. And so I should say there's no finite group theory in this so far, and a theorem like that would obviously require some finite group theory.
Can you construction with Greenland exist for linear?
Yes. Yeah. No, so I can do. You mean the basic construction? Yeah. Yeah. You can make these linear if you want. Yeah. Yeah. And how do you do that? So actually, the groups I described, we now know are actually linear. We didn't know at the time because you do the RIPS. So remember, this is a product. This in the original construction, this is a product of small cancellation groups, the big group. But you can make them small cancellation as strict as you like, and then by Y's they can be cubulated. By Agol they're virtually special, and so you can actually make it linear over Z. So you can actually realize these are subgroups of GLNZ for large N.
Are there interesting properties for which it would be an open question whether they are very solvable or not?
I'm sure there are, yeah. Yeah, this was I've been obsessed with this one for quite a while, so I can't. Yeah, well, there's these variations that we're talking about families of finite quotients. Sorry, I'm sure there are, but my mind's gone blank. I can't think of what else I want to solve. Does anybody else have any suggestions? I'm not sure.
Okay. Any more questions? No, so, okay, so let's thank